All right, well, thanks for the invitation. Yeah, so today I'd like to tell you a story about this particular manifold I call the banana manifold. I've become somewhat obsessed with this over the last year or so, to the point where I worry that the young mathematicians are snickering behind my back. They're going, Bryan, obsessed with the bananas. But I'd like to point out, I'd like to show you that I think this connects to a lot of things we've been seeing last week and whatnot.
I think they mostly snicker right in front of you.
Well, that's true. That's true. Okay, so I'm going to be interested in partition functions, Gromov-Witten, Donaldson-Thomas. So I'll be particularly interested in Donaldson-Thomas, but if you're more on the Gromov-Witten side of things, remember that they essentially contain the same information. These are partition functions, as we all know, that contain enumerative information, and also have this connection to physics, which gives them this kind of rich structure. They are virtual counts. They're made up of, these partition functions are made from numerical invariants, and these numerical invariants are some sort of virtual count of curves. And as I said, the two theories, Gromov-Witten theory and Donaldson-Thomas theory, conjecturally contain the same information. These are theories about Claviau threefolds, and we now know this conjecture to be true for quite a broad spectrum of Claviau threefolds. But it actually won't, it's not clear, we don't have it for the particular manifold I'm going to talk about, at least not immediately from that, but such a little caveat. Okay, so let's get to the specifics of what we're talking about here. So these are theories about Claviau threefolds. So for me, a Claviau threefold will be a complex smooth algebraic variety dimension 3 with trivial canonical class. And I'm interested in a virtual count of curves. I'm interested in counting curves. And so there's a couple different perspectives on curves as subject. In Gromov-Witten theory, the perspective is viewing curves as being parameterized by maps. Or we can view curves, Donaldson-Thomas theory views curves as being given by equations. So in other words, as subschemes. And of course, we have a very old natural parameter space, a scheme, in fact, that parameterizes subschemes, which is the Hilbert scheme. So the Hilbert scheme will be using parameterizes subschemes of X of dimension 1, so by which I mean the cycle associated to its highest dimensional component is given by some element in two-dimensional homology, degree 2 homology. And the other piece of information we keep track is the holomorphic Euler characteristic of the structure sheaf. So if this is a smooth curve, that's of course 1 minus the genus, so it keeps track of genus. But subschemes in threefolds can also have a lot more complication. It could have nilpotent thickening, it could have singularities, it could have embedded points, and so a lot can happen. And in fact, there's sort of no way to avoid that phenomenon when you go about counting curves in this way. So I keep calling these invariants. They are invariant under deformations of X, and we're going to build them right out of this Hilbert scheme. Okay, so here's a definition. So let's see. Let me go back for a second. Let's think about what we would want to do if we wanted to count curves. Well, so obviously, if this is a finite set, this Hilbert scheme, then the count ought to be just the number of points in that set. And that would be the number of curves of class beta and Euler characteristic n. Now, that clearly isn't going to be deformation invariant, or at least it's easy to imagine deformations that take two curves and bring them together into a single curve, and in which case that Hilbert scheme, if it had some finite set of points would come together and you'd have 2 points turn into 1 point. So this Hilbert scheme is of course a scheme, and it would remember that 2 points come together because there'd be some thickening. So however we're going to count this, we certainly need to keep track of the scheme structure of Hilbert scheme, not just its, say, underlying topological space. However, what we're going to do is actually one of the most naive ways you might generalize the count of a finite set to spaces, which is the topological Euler characteristic. So the topological Euler characteristic is an integer invariant, and it's certainly in a finite set, just counts the points. But because we need to keep track of, nilpotent structure in the Hilbert scheme, and in fact singularities of the Hilbert scheme, we're going to do something slightly more complicated, which we will do a weighted Euler characteristic. So what is this? So little e here is just the topological Euler characteristic. And when I say weighted by a function, by a constructible function, what we do is we add up the Euler characteristics of the level sets of that function, and we multiply by the value of that function. So the function is, of course, the Bryan function. It is something that is defined for any scheme over C, and it's a measurement, just a single numerical measurement of singularities or nilpotent structure. It only depends at each point on the sort of formal local singular structure. And it turns out that that particular course invariant is enough to get a deformation invariant, the theorem of Chi-Bryan, when you weight the Euler characteristics in this way. But the lesson here is that this is very close to something very naive, the Euler characteristic. In particular, we get some moves with the Euler characteristic that, for example, you don't get in Gromov-Witten theories. So Euler characteristic is motypic. It means that you can compute Euler characteristic by splitting your space up into strata and calculating the Euler characteristic strata by strata. It also behaves well with respect to group actions. If you have a group action, say like a C star action, the Euler characteristic of a space with a C star action is the same as the Euler characteristic of the fixed point set. So we have a couple moves available to us here, but the price we pay is we have to keep track of this Bryan function. Okay, so let's settle that. Okay, so that's the basic invariant. It's defined for any Claviel threefold. Actually, it's deformation invariant for proper compact Claviel threefolds. But the deformation makes perfectly good sense even for open threefolds, as long as we take that Hilbert scheme to parameterize curves with proper support. The Hilbert scheme won't be proper, but we can still take its weighted Euler characteristic. Now, of course, the way that these numerical counts really come alive is when you put them into a generating function. So, as we usually do, we package all of these into a single object, which is a formal power series of some sort. We're going to run over the classes in homology and all n and keep track of things with variables q and p. I put a minus sign in there because it turns out that makes everything a little bit nicer later on. Sometimes we might want to only keep track of some of the curve classes, so we might want to introduce a sublattice here of curve classes and only count curves in that sublattice. So that would be like setting some of the variables equal to 0. So indeed, if you pick a basis for the curve classes, and you can do so such that any actual effective curve is a positive multiple, then you see that this guy is a power series in Q, formal power series with the same number of variables as the rank of your lattice. And the coefficients, well, because for a fixed homology class, the Euler characteristic can only be so negative, so this is a formal Laurent power series. The coefficients are formal Laurent series in P. So that's the structure of what this thing is. And as I said, this is where the invariants really come alive, is studying this formal function. And in fact, what we'd really like to do is think of it as an honest function. Although as defined, it's not clear when it makes sense as an honest function. But a lot of the important structure and properties that come to us in the form of this thing actually being a function. So for example, the correspondence between Donaldson-Thomas and Gromov-Witten theory, you can think of Gromov-Witten theory is also given by a a formal series. You can think of that as being a Taylor expansion, and the Donaldson-Thomas series is like a Fourier expansion of the same function. So you're going from a Taylor expansion to a Fourier expansion. That involves analytic continuation. You'd have to know that this thing is somehow, for that to be defined, really a function. There's other properties that we now know. So for example, these rational functions, or sorry, these formal Laurent series are provably, after we do after we get rid of the degree 0 part, are provably rational functions. So that's another instance of some sort of property of all the invariants taken together. And then something relevant for us today is these often, and these have some sort of modularity property. So these functions might look like modular forms or Jacobi forms and things like that. Okay, so here's sort of one of the embarrassing secrets of this subject. We actually don't know this partition function for a single compact Labial, not even conjecturally. We don't even have, I don't even think on the DT side that we have even an algorithmic way to completely compute one. So we really don't know it. We're kind of in the dark on these guys.
Sorry, what about K3 times elliptic curve?
So we know ones where the partition function is basically 0.
Oh,
so
sorry.
for K3 across an elliptic curve or an abelian surface, these are deformation invariant. You can deform when there's basically no curves. And so you get 1 because the Hilbert scheme of the empty curve, the 0 curve class and 0 point is the empty set, and the empty set is a single point. So anyway, these are 1. So not counting those, we don't know. Now, there's an interesting story for K3 and for an abelian threefold, which is that there's a modified version of this. And in fact, for the abelian threefold, that's the only place where we conjecturally have a complete answer for the full thing with some strong evidence. But that's for a reduced, that's for a modified DT invariant. Okay, so and remember back here I said that well, maybe we can be a little less ambitious. We can set some of the variables equal to 0. Even if we do that, even if we restrict to some sublattice, there's very little we know. We basically only know it for one-dimensional sublattices of a very certain type. So when you've got, when your Claviau is fibered by K3 surfaces, and you're looking at some curve class and its multiples, which is supported on the fibers, then there's a theory due to we all know how to say Pandora, and Thomas in there too, which basically reduces it to a local version of K3, which is where the formula is this very famous Katzklem-Vafa formula. So we have it sort of for that, and then an even slightly simpler case is when your curve class is just the fiber class and its multiples of an elliptically fibered X. So there's actually still very, very little that we know. And in these cases, actually, the thing that we do know has a lot of really interesting arithmetic properties, some sort of automorphic properties. Right, so in this list, you might notice these are things that are fibered by Calabi-Yau's, right? So it's either fibered by K3 or elliptic surface. The one that's missing here is abelian fibration. And so the example I want to show you today is in fact, it's a specific Claviau threefold, but I think the story for this will generalize to other abelian fibrations. It's a specific Claviau threefold I'm going to show you that is fibered by abelian surfaces. And it's actually pretty special in that the Picard number of the fibers is 3. So I actually have a 3-dimensional lattice fiber classes where we can write down the entire partition function. So I'm going to tell you that story, and part of what the interest here is we're going to see that that partition function, once I compute it and write it down, has some kind of remarkable properties. It's going to be connected to number theoretic objects. In fact, Siegel modular forms. I wrote Jacobi, but it's actually even more. It's Siegel modular forms. And then another real surprise is that it's related to a seemingly unrelated geometry and an unrelated concept. So not, particularly the elliptic genus of the Hilbert scheme of points on C2. Okay, so a well-studied symplectic manifold. Okay, so I should now define this guy. It's built out of pieces that I think you all probably know very well. The first piece is a rational elliptic surface. So there's a picture of a rational elliptic surface. One easy way to define it is as a hypersurface in P2 cross P1 that's degree 3 on the P2 factors and degree 1 on the P1. So if I project that surface to P1, each fiber is a cubic, so I get this fibration by cubic curves, elliptic curves, with 12 singular fibers, it turns out. And if I project on the P2 factor, we realize it is a blow-up at the 9 base points of that pencil. And so it's also this rational thing. It's a blow-up of P2 at 9 points. So pretty concrete guy. So concrete we can draw a picture of it. There it is. Okay. Okay. So here's the banana manifold. So what I can do is I can take a fiber product of this elliptic surface with itself over P1. So over each point in P1, I'm just getting the product of the fibers. Okay, so the Cartesian product. So that gives me something that's fibered by abelian surfaces, really special ones. In fact, elliptic curve cross elliptic curve. But on these fibers here, where the node was, at the point which is node cross node, in that fiber product, that's now a singularity. It's a conifold singularity. And so we want to just resolve all those conifolds. And one way to do that, to make sure that it's a projective conifold resolution, is one sort of global way to resolve them all at one time, is to blow up the diagonal. So you don't see blow-ups of divisors very often because it usually doesn't do anything, right? A blow-up of a divisor doesn't do anything outside of the singular set, but at the singular set it will give me these conifold resolutions. So it turns out that this guy is a Claviel threefold. Here's its Hodge numbers. It's got 8 deformations coming just from the deformations of the rational elliptic surface. That's everything. It's got a bunch of curve classes. So it's got 3 curve classes in the fiber. And then it's got 17 sections worth, 17 independent sections. Okay. This is not, I haven't been able to find this on any of the lists. It is a conifold transition away from a well-studied Claviel threefold called the Shane-Claviel threefold. But in particular, it's not a complete intersection in a toric variety. I don't actually know what its mirror is, and I'd be actually very interested if anybody could figure out what its mirror is, or how to count it even.
We're bananas.
What's that?
We're bananas.
Yeah, the bananas are coming. Okay, so the bananas are coming. Let's see what happens to these singular fibers after we resolve. Yes?
So those 12 points in the line, how constrained are they, if at
Oh,
all?
yeah, so that's a fun story about rational elliptic surfaces, right? So the 12 have like one constraint. You can get down to 4 points so you can bring them together, but you can't get any further than 4 points. So there's one constraint, and that's an interesting divisor inside of. Yeah, Robbie's witness.
So there's 8 parameters.
Yeah, that's right. That's the 8. Good.
Oh, good. Okay.
Yeah.
So if it's conifold transition away from something we know, then why don't we know its mirror or even the shell?
Well, so that's actually part of this, is that if somebody understands how to go, it's going kind of the wrong direction, but maybe you know how to do that on the mirror side. I mean, yeah, I think in principle we know what is mirrored to the conifold transition. The Shane is self-mirror, so you'd have to do the opposite. Yeah, okay. So where are the bananas? So those are it's in the fibers here. So okay, as we discussed, it's an abelian surface vibration where the generic fibers are just products of smooth elliptic curves. Let's just think about for a second what happens on a singular fiber. So in the rational elliptic, this elliptic curve is a rational curve that's glued at 2 points in non-normally. So you can think of this is actually this curve is a non-normal toric curve. It's toric, it's got a C-star action on it, whatnot. And I'm taking the product of these two guys, so I get something that's non-normal that is toric, and then I do this resolution. So when I do the resolution, these 2 points will come apart, that'll give me one curve. These 2 points will come apart, that'll give me another curve, and then the conifold curve itself gives me a third one. And so what we see is these singular fibers, they're non-normal toric varieties, so they're compactifications of C star cross C star, and it's got 3 curves at infinity, and each of those curves is a P1 with, which is a -1 curve, so you know, a conical curve, and they meet at 2 points at 0 and infinity, and they all meet there. So this case thing kind of looks like a bunch of bananas. There it is, right? The one thing about this drawing is that this, well, it's not so bad here actually. The way that they meet is like the coordinate axes in C3. So formally, locally, this is the 3 coordinate axes in C3. So that's what I call a banana configuration. And actually this has been studied, this sort of local configuration was studied, well, I think more than one place, but at least in a paper by Denis and Abuzayed and Ludmil maybe. So who studied this, in fact studied mirror symmetry of this local configuration from a SYZ perspective. In fact, let me come back to that in a second. Yeah, so I wanted to tell you a little bit of, if you sort of follow through carefully on what happens on that singular fiber, if you take its normalization, you'll find that you get, well, P1 cross P1 blown up at 2 points, or you can think P3, P2 blown up at 3 points. And the normalization, when you reverse the normalization, it glues boundary curves together. So there's the picture. So a lot of you might recognize that polytope as the moment polytope of blow up of P1 at 2 points. And then these are the torus invariant curves. Melissa was drawing pictures like this yesterday, and this is what happens in the normalization. And of course you can see that in this surface, these are actually -1 curves, and when they glue, you get the 2 -1 directions. Another way to draw this, if you want to think sort of particularly about that configuration, is if you draw a single one of these guys. So again, Melissa was drawing this picture yesterday. This is a conifold here. This is sort of the toric diagram of the conifold. But in this situation, in this geometry, this leg is being glued to this leg, and this leg is actually the same as that leg. Now, if we do what Melissa was doing, which was drawing the mirror curve, we got the mirror curve sort of heuristically like that. But now notice that this right here is glued to this right here, and this right here is glued to this right here. So that's in fact a genus 2 curve. The mirror curve of this local configuration is a compact genus 2 curve, which we'll come back to in a second. That's again this local picture, and that's the mirror, I think, in this, well, the sense in which that's a mirror. Should probably read Denny's paper. Okay, but so we will come back to that. But that's a good picture to have in mind. Okay, so those three bananas, there's 12 banana configurations, but in fact there's only 3 curve classes. They all match up in homology. So those curve classes generate the homology of the fiber. And there's an important quadratic form, which is, you should roughly think of as if I move those curves to a smooth fiber, then that's a form manifolded as a quadratic form, and this is the quadratic form written explicitly. And what is the theorem? So the theorem is that partition function, that generating function, so now it's got 4 variables, the one that keeps track of the Euler characteristic, and 3 variables keeping track of the degree of the banana curves. And the theorem is that there's this product formula where the coefficients, first of all, which I'm going to tell you in a second, depend only upon the k and this quadratic form. So the dependence on the curve class only comes to this quadratic form, but in the exponential. And that quadratic form as given, and these coefficients, which depend on two variables, if you write their generating function, you find you get a quotient of theta functions. So these are theta functions if you think of q as e to the 2 pi I tau and y as e to the 2 pi I z. This is sort of the usual, two of the usual theta functions.
Are all the banana curves in each of the 12 singular fibers equivalent?
Yeah, so sorry, that was, I said, at the top line, they generate p curves. So in fact, so they're all in that same lattice, and in fact, they all match up. Like all the conifolds all the ones that were conifold resolved are equivalent. All the ones that came from one surface are equivalent. All the ones that come from the other surface are equivalent. Yeah, I mean, another thing that's just kind of an aside is these are all -1, curves, so you can flop any of them. But if you flop any one of these, you actually get right back to where you started. You get another banana configuration. And if you run the flop formula on this thing, what you find is that that gives you like a rationality in these q's as well. Q goes to 1 over q is a symmetry of these things. So there's that's a bit of an aside. Okay, so we see some modular properties coming in already. So this thing, in fact, it looks sort of like a Borcher's lift, where you've got, if that means anything to you, it's you've got modular form. The coefficients of some modular form now appear as the exponents in a product.
Does demanding invariance under that q goes to 1 over q in each variable pin this down to some relatively small ambiguity, or is that just something you observe afterwards?
That is something you can observe afterwards that has to do with symmetry of this, but it certainly doesn't nail this down. These particular coefficients have a lot of rich structure here that, hard to see. They're actually just hard to see. You have to compute it. So let me say a couple other things that's remarkable. So I have this connection to these automorphic properties. Here's the other crazy thing that is sort of hard to understand without just computing it, is that after I throw away a few prefactors, things like McMahon functions, and then I do kind of a change of variables which breaks this symmetry of the Q1, Q2, Q3, I end up with exactly the generating function for the equivariant elliptic genera of the Hilbert scheme of points. Elliptic genera is something that has two variables, q and y. It's a one-variable generalization of a chi-y genus, which is a generalization of Euler characteristic. So that's two variables. If I'm doing it of the Hilbert scheme, I need some other variable to keep track of the points in the Hilbert scheme. And because this is non-compact, to actually define the elliptic genus, I need to do it equivariantly with respect to the anti-diagonal action, so I get an equivariant parameter. So this thing has 4 variables, and under a change of variables, you end up getting exactly this thing. So that's also sort of surprising that I'm going to show you where that comes from, at least in terms of my proof, but it's still a really kind of bizarre connection of geometry. I mean, there's some physics that I'm going to talk about at the end.
So where exactly, what's the word, level, is that theta function?
Yeah. I mean, I think this one is for, for the either gamma 2 or gamma 4 congruent subgroup. But then otherwise, I think this is weight. I think this is weight one half level 1, and this then is weight 2 level 1 or something like that. I mean, yeah, to be honest, I haven't. There's going to be I'm going to make another statement that is a little bit easier to parse. I'm not exactly sure about the specifics of the modularity of that particular guy. There's no good excuse for me not to know that, but I should. Here's something that's even kind of cooler and maybe connects directly to this guy, perhaps, which is you could say, well, okay, we actually don't know the Gromov-Witten-Donaldson-Thomas conjecture in this case, but let's run it as if we did. What does it say about the Gromov-Witten theory? So, well, how does that connection work? Well, you have to get, so the prime just means you get rid of the degree 0 piece. And then you think of Donaldson-Thomas theory as a connected theory, as a disconnected theory, and Gromov-Witten theory as a connected theory, so that's why they're this log. And then as I was telling you, you should think of Gromov-Witten theory as a Taylor expansion and Donaldson-Thomas theory as a Fourier expansion. This is the MNOP change of variables. But when you do that, you get now the Gromov-Witten potential. So here you can fix a genus when you look at the coefficients of this, and those will be variables of those will be functions of 3 variables, which are my curve classes. And it turns out, just from playing with modular forms and with power series, that these guys are all meromorphic genus 2 Siegel modular forms of weight 2g minus 2. So what does that mean? These things are functions on the moduli space of genus 2 curves. Well, they're meromorphic sections of a line bundle of degree 2g minus 2 over the moduli space of curves, which is 3-dimensional. So these are like coordinates on the moduli space of curves. So I mean, this was worked out by a student of mine following, I think, advice or hints or maybe recipe from George Operdijk. But I find this kind of intriguing because it'd be nice to understand that as in terms of this. So, if this is supposed to be a mirror of that, then I would expect the complex parameters of this thing to correspond to the Kähler parameters of that. So I've got the Kähler parameters there, and now they look like now complex parameters on the genus 2 curve. Okay, so that would be nice to really understand in some detailed way, but that is a fact.
Jim, there's a physics paper on Iqbal, Hollywood, and Bach some 50 years ago.
Yeah.
I relate this kind of picture.
Well, that's right. So I'm going to talk about that paper a little bit. Yeah.
Is this a way to somehow understand this here?
Yeah, we'll see that this geometry. Yeah, I'll get to it a little bit. In fact, that's where we're headed now. So why are we seeing? Okay, so we give some sort of heuristic about about why we're seeing modularity. Why are we seeing elliptic genera? So and let's do some geometry here. Yeah.
Actually, sorry, do you know what the first few of those FGs are? The genus 2?
Yeah, Stephen's written them out in.
Okay.
This is a master's student of mine, and he's writing a master's thesis, and he has the first few. And what you do know is that there's like a universal.
Whatever Kaitan or something?
Well, there's a. I think it's not Chi-10. It's one of the generators of lower. It's a different generator, but there's one is there, and then it's multiplied by just ordinary modular forms, which is what's changing the weight, and you know the weight of that thing that's being multiplied by, but then you have to sort of go term by term to determine which one it is, and they've got sort of complicated linear combinations of the modular forms we all know. So yeah, and that's the sense in which you can actually write them out. Yeah. Okay. So let's do some geometry. So what are we trying to do? We're trying to compute this weighted Euler characteristic of the Hilbert scheme of curves on this guy, and we're looking at curves homologically supported in the fiber. So Hilbert schemes can be very complicated. They're usually very singular, non-reduced, sort of everything that can go wrong does go wrong because you're parameterizing curves that in general have nilpotent structures sticking every way and points and whatnot. But one thing that we do know about this is that because these are supported, because it's homologically in the fibers, it turns out that they have to at least be set theoretically contained in some collection of fibers. Now set theoretically means that it still could have nilpotent structure pointing in. So the thing that you can actually say is that is that it's supported on some finite set of formal neighborhoods of the fibers. If you want to think analytically, you could think little analytic neighborhoods. And so because of this motific nature of Euler characteristics, you know, we've got strata. The strata are parameterized by configuration spaces. There's sort of a whole calculus to do this, which boils down to what I really need to understand, is I need to understand the Euler characteristic of this thing, which is still very, very complicated. And remember, moreover, if I want to keep track of that Barron function, I have to remember the singularities that come from here. It's the Barron function here. So I can't quite just look at some strata. I actually have to look at a formal, or if you want, an analytic neighborhood of this guy, so that I know what the Barron function is. So this is really the thing that I need to understand. The Hilbert scheme of subschemes contained in some formal neighborhood of a fiber, and I need its formal neighborhood inside of the big Hilbert scheme. So remember, we had this sort of other action. Oh my God, is that readable?
No.
Not really.
All right. Don't fall asleep.
Oh.
Just for a moment, temporarily. So remember, I talked about for Euler characteristics, you also have this other move besides stratifying, is that if you have group actions, it makes your life very easy. So we can look for a group that acts here. And because this thing was actually, away from the bananas is a group scheme. So this X is a group scheme over the base. And I can make, so that basically means that the fibers are groups, right? Away from the banana, the group is C star cross C star. They don't act on formal neighborhoods a priori, but there is something you can make, a much bigger group you can make that does act on it. So if you're thinking of a little analytic neighborhood, you can think of the group of sections of this guy, and then you can add by a section, and that indeed moves the entire neighborhood. So what kind of group is that? Well, you can restrict the section to the central fiber, which is a group which is either E cross E as a group or C star cross C star. And so that's what I call this thing right here. And that restriction makes it into an extension by the set of sections through the origin, which is this big, if you're doing it, it's an infinite dimensional group, but it's basically a vector group. So it's an extension of this central fiber by a vector group.
I'm so distracted because this is the first time in my life I've ever seen a slide in ultraviolet light. But why is there just, what's that spec C epsilon there? Why is there just one parameter? I'm a bit confused.
Well, because I'm focusing on one, so that's this.
Oh, because the normal.
So I'm looking at sections
because
of
the
this
base
guy
is
over
aligned.
that.
It's because the base is aligned, and you've chosen.
That's right. So then, if you want to think analytically, you can take a little analytic disk, and I can look at
And you've chosen
sections
a
of that.
coordinate. Okay, good.
Okay. So that's a group that acts. Not only does it act on this strata, it actually acts on the entire formal neighborhood. So it respects the Barron function. So I can use it to do Euler characteristics. And whenever you have a free action by a group, well, as long as the orbits all have zero Euler characteristic, which is true on the smooth fibers, you'll just get zero for the Euler characteristic. So this, very quickly, you actually get down to this local case. You realize that the only thing that contributes are the singular fibers. And there, the group is an extension of C star cross C star, that's the group of the singular fiber, by an additive group, and all such groups split. So we actually get an action of that's the one case where you get an action of the fiber on its formal neighborhood, which is kind of weird, but it's true. So in fact, I even had to write it out in coordinates to convince myself this argument was really correct, but yes, it's true. So we get an action on this thing, say those are now singular fibers, and that's really, I think I'm back to yellows. No, I'm not. So much for the yellows. Okay, so what does this do? So if you analyze the fixed points, so this fiber in fact, its formal neighborhood, a good way to think about it is it's a non-normal toric formal Claviau threefold. It's got this torus action, the C star cross C star, that in fact acts preserving the canonical. And it's folded up compact, the neighborhood is smooth. And so the fixed points are the same, it's the same story as you have for a global toric Claviau threefold, which are never compact. The story is that the fixed schemes are all monomial subschemes. So they're isolated, and they're given by this kind of combinatorial data. It says that that they're supported completely along the torus fixed curves, namely the bananas. They're supported on the bananas, and along the, what would you call it, the meat of the banana, it's given by a 2D partition. So common story from Hilbert scheme points that monomial ideals in two variables, which would be the transverse variables, are in one-to-one corresponds with 2D partitions. And then we can have a bunch of embedded points here. And so you can think of each of these as the corner of a room, and the monomial ideal corresponds to piling boxes in there. And along each axis, those boxes go to infinity with profiles given by these partitions. So this is a story that anybody who sort of knows the toric story for Claviau threefolds knows well. We can now compute this partition function by counting these objects. And there's a really important point here, which is that, so we get down to points, we still have to know the Barron function at those points, which remember involve that whole formal neighborhood. So luckily there's this theorem of Barron-Fontecchi. If you've got a C star cross C star action, well, just any C star with isolated fixed points acting on the symmetric obstruction theories. So in this case, we're using the symmetric obstruction theory associated to that formal guy. Then you can determine the fixed points. You don't need to know the singularity extremely well. You just need to know the parity of its Zariski tangent space. Okay? So we can just count combinatorial configurations with a sign which is actually computable. Okay, so let's do it. Okay. So what are we going to do? We're going to count up configurations. Configurations are given by this data of 3 partitions. So I'm going to sum over the partitions. And then I have to have something that counts the ways of piling boxes into the corner and counts the ways of piling boxes into the corner. There's a universal object called the topological vertex which does that. So what it says is that for each fixed point, I need to count that fixed point with a sign, which Barron-Fontecchi tells me it's that sign. And then, of course, I have to know what its holomorphic Euler characteristic is and what its curve class is. Those are fairly easy to do just from the geometry. And counting those is the same as counting these combinatorial objects. And the key thing here is this universal topological vertex, which counts basically monomial ideals in C3 with the given asymptotics. Okay, so that's what those guys are. The prime means conjugate partition. If you think about the way they have to glue up, that's what it is. So this is this kind of enormous combinatorial product. The 12 is up there because there's 12 of these things, 12 fibers. Reshetikhin-Akunkov and Vafa have an explicit formula for this combinatorial thing in terms of Schur functions, or another way you can think of it is in terms of matrix coefficients of a certain operator on Fock space that you build out of vertex operators. I don't mean to say that just to be like fancy, but there's actually, this tells you a little bit about how you can go about you see this is like a partial trace here. It tells you a little bit about how you might manipulate those Schur functions and simplify this expression. So that's all buried in this little green sentence here, which is that I can do that trace over 2 of the indices. And so it boils down, if you want to think about it in terms of Schur functions, to this like 5-page set of identities of Schur functions that eventually get me down to something that's a little bit simpler, which is, it's still a sum over partitions, but this thing is now a product formula. It's a product that involves, it depends on this lambda 1 and these variables. And the way its dependence on lambda 1 is through the hook lengths of the partition. So if anybody's thought about the Hilbert scheme of points, they, on C2, they know that the weights of, they know that the fixed points of the torus action are also in bijection with the partitions, and the weights of the tangent space in the Hilbert scheme at a given point is really determined by the hook lengths. And here's where this kind of miracle that I'm going to talk a little bit more about happens, which is you notice, quote unquote, that if you make a change of variables, and again you have to throw out some prefactors, that had you gone and computed this guy by localization, so that would be a sum over fixed points, which would be a sum over partitions of something that you compute that involves hook lengths, you notice that these two guys are the same, again, after a change of variable. And maybe getting rid of some prefactors. So this miracle is, of course, does come from physics under the guise of geometric engineering. So this is the paper that you mentioned earlier. It has to do with, well, in this particular case, it has to do with a 6D duality. So there's a 6D theory, which gives me, I've got a 4-manifold, and I think we're compactified, where we product by 2 circles, which is why elliptic genera come to the game, and it's some gauge theory on that 4-manifold, which in this case is just this C2, and the gauge theory gives rise to these Hilbert schemes. And then on the other side, there is a string theory, which, so they don't use this geometry, but they write down this kind of formal string theory, and they do have a discussion in terms of this curve, which is exactly this guy. So this was certainly noticed in the physics literature, and now what have we gained? So we've renamed that guy. We haven't made the actual sum any better. It's still a sum over stuff, but we've simply named it something else. But now there's another move we have, which is actually a deep theorem of Lipkovner and Borisov, and then you need an extension to the equivariant case by Walder. I should have written that. Which says that the equivariant elliptic genus, the equivariant elliptic genus of a Krepin resolution is equal to the orbifold equivariant genus of an orbifold. So we're using the fact that this Hilbert scheme is a smooth symplectic variety, which is a Krepin resolution of this orbifold. Okay, so this is sort of non-combinatorial. This comes from motific integration. So it's kind of a deep geometric, fairly deep geometric result that gives rise to a really concrete combinatorial identity. Because if I do localization to compute this guy here, now instead of having a sum over partitions, I have a single fixed point. And suddenly that calculation becomes much easier, and you get an entire product formula. So that's localization there. And that's what leads to this form. And these coefficients, the way that kind of works is this symmetric product in the localization exactly puts up in the exponent the underlying elliptic genera of the underlying C2, which you can just write down, again, in terms of theta functions, and that's where these guys come, and you have to follow through all those change of variables, and you see the quadratic form showing up. You see the symmetry being restored, right? These 4 variables are all very different. They're on that board over there. But, so there's this sort of wild asymmetry here, but when you put it back together, you get, you see this magic symmetry. Okay, I think we'll stop there. Thanks.
Are there any questions or comments?
Yeah, if I turn on the other source parameter,
Oh, I thought you turned on. Which one do you want to turn on? Yeah, you turn on the which.
acting on C2 here, so it's
Yeah.
acting on C2. Is there a way to see that from these vertex combinatories?
Right. So here's what you might hope. So there's another parameter you could turn on here. It kind of destroys the Claviaunus, but okay. And now instead of hook links, you get arms and legs. And what you might hope, and I don't know if this has been checked. It might be that you might hope that if you had started instead with the vertex, you had started with the refined vertex and put it together in a clever way. You might hope to get there. I haven't done that. I don't know how to define. I mean, the reason is because I started from this compact geometry, and I don't really know how to define the motivic invariance of that guy so that it relates to this refined topological vertex. But that's kind of the guess that you would have.
Okay, Ben?
Ben.
Similar question. What does P become?
What is what?
What does the variable P become?
Okay, you're making me remember the chain of variables. Yeah, I think it's so the Q1, Q2, and Q3. Let me call. So it's like Q1, Q3 is one of the variables. Q1, Q2 is another one of the variables. Q1, and I think the P just becomes the T. It either becomes the T or it becomes the Y. No, the P becomes the Y. So this is P. So it's the chi Y part of the it's the Y part of the elliptic genus. And then these other guys exactly how they match up. Maybe this one is that.
What happens instead of taking S cos X, S cos S over P1, you take the S cos translation of S?
Right, so then you get this Shane manifold.
Oh.
So that's got sort of 1919, and what happens is, at least in the fiber classes, you get nothing, you get basically nothing. Because now the singular fibers have an elliptic curve in them as well. And so you basically get nothing. That's an interesting, it's an interesting manifold to study. In fact, has been studied where you, instead of looking at a sublattice, you look at an affine lattice. So fix a class, fix a section, and then add up fibers, and you get very interesting things. So this is a conifold transition away from that Shane. So in particular, given the partition function of this guy, you can go backwards and get the fiberwise partition function of the Shane by setting the conifold variable to 1, essentially. And it's this fun exercise to see that when you set one of those variables equal to 1, so you get a sum up here, everything wildly collapses and you get basically nothing. You get just a couple of easy terms.
So to clarify, when you say it's a conifold transition away, you mean 12 conifold transitions away?
Well, it's one conifold transition which affects 12 curves at once. Sometimes when you do a conifold transition, like if you're creating one conifold, you might be forced to create other conifolds at the same time.
Okay, so you're doing 12 at the same time.
Yeah, 12 at the same time, and that's sort of why the Hodge numbers behave the way they do. It's the constraints on moving to and from. Yeah.
Okay, if there's no further questions, let's thank Henry.